Yeah, we've missed the summary. I know I'm not recording, but sorry about that. You missed the summary. Then I'll just go over it again. So transportation will be network analysis. Are you okay? So network analysis. Okay. So anytime you talk about network analysis, you know that you use this to support your transport. Are you okay? So we have what we call GIS as GIS transportation in transportation. All right. So we can apply GIS to, you know, other areas in our lives. Are you okay? So all that comes under application. All right. So I've chosen to talk about network today, and then maybe I'll talk about 3D analysis. We are almost done. I mean, honestly, I don't really like talking a lot. Okay. A word to the wise is enough. Mm? A word, one word is enough. So the summary of everything that we're talking about is what you see on the screen: layers, components of GIS, talk about topology, data sources, map projection, data models. Here we talk about raster and vector data sets. So this is where the raster comes in. Now, in spelling raster, if you're not careful, you end up writing the raster man. Are you okay? So Rastafarian we're talking about here. Talk about vector, points, lines, polygons. Okay. And then raster is squares, a picture. You need to have this in your mind. It's very simple, and I think it is simple. You can remember everything that we talked about at a go without even memorizing it. Are you okay? It's a summary of it because it's a story. Every story, if you follow it, you get to the end and you can ask questions. I mean, I have nieces that I always tell bedtime story. They'll ask you questions. What happened to the rabbits? Are you okay? So we're talking about a few other application areas. That's what I want to draw your attention to whilst we talk about network analysis. I want you to understand that it's an application area, and we started the whole lecture, okay, by talking about application areas. So network analysis is what we want to talk about today. Okay, so we need to recognize that networks exist around us. Are you okay? So networks, drainage networks is one of them. So it's not only when talk about network, or do you have network? Normally people are talking about phone. Are you okay? So that in that case, talking about communication network. Are you okay? All right. The telecommunication network. Are you with me? In that it's made up of users and then transmitters, and of course the users are receivers. So your phone is a receiver. That's why you shouldn't hold it too close to your head. Are you okay? But obviously, when we talk about networks, they are all around us. Networks are all around us. Talk about road networks. Okay, so roads. Can talk about drainage. Can talk about pipes. Okay, so pipe networks. For you can talk about rail. Okay, this is one of the areas where, honestly speaking, it's interesting. I kind of love the area, just that I haven't really done a lot of work in network GIS, but obviously it's really fun to be able to look at the whole system and then and to analyze and to see where the problems, the bottlenecks are. Are you okay? But what really is a network? So you can go on and on. Are you okay? If you are able to understand what a network is, you're able to identify one, you're able to see what really makes it a network. What makes a road network, you know, a network? Okay, let's take this as an example. Okay, so if we have a road network and there's a crossroad, we have a crossroad. All right, what really makes it a network is the fact that you can actually move in one direction, okay, and then get to the other direction. You can actually move from point to point. In other words, these are actually nodes, okay, and then goods, are you okay? Services, data, are you okay? Material can move along the link. So we have a link or an edge. Okay, so link, segment, an edge, all these kind of describe the physical network on the ground. So remember that in GIS, you're only modeling the reality. All right. In GIS, we are only modeling what the reality. The reality on the ground doesn't look like this. The rail is a metal. It's not really one straight line like that. But then this is how we've modeled it because it's of a linear extent. This is what a student is supposed to understand. The GIS student is supposed to understand that we are modeling something that is on the ground. Okay, so here, this is a vector. You need to understand that this is vector. Why? Because vector models the world, the real world, as well points, lines, and polygons. Okay, so the link is there. Then we have the nodes. Normally, the nodes also become the so-called. So if you take an example, like a junction. Okay, we talk about Malam Junction. We talk about Clapham Junction in London. Anyway, yeah, I think I'm getting a bit emotional on that one. But obviously, you can see that that's why junctions are important. If where the issues are, it's always going to be a junction. When you have a problem with your pipe network, your plumbing work in the house, it's always going to be at a junction. Are you all right? Because that is where the essence of the network, or the at the center, at the heart of a network, is those little points that really where there's a join, where there's a join. All right, okay. And so topology, you need to have a topologically correct data set. If you don't have a topologically correct data set, you can't do a network analysis. It's very important for you to know that. Let's go to our PowerPoint and see if there's something there that reinforces. So obviously, I've given more examples here. Okay, and even other glaciers. So it depends on how you look at it. Okay, so yep, there you go. Networks are used to move people, transport goods. Put that in your mind. There's got to be something moving on the network. Otherwise, then I wonder what a network is. Okay, it's not really a proper network. So the reason we call the road network is because cars are moving on it. Is all right. But when you have human beings moving on a road, there's a problem. Okay, they only cross it. All right, so communicate information sometimes can be, we have what we call a network engineer. A network engineer in IT, like Charlie, he's really a specialist. Are you with me? And they understand how the packets of data is moving from your computer to the other computers, through servers and all that. They are also networks, and they can be, equally modeled. They control the flow of matter and energy. Are you okay? So sometimes talking about drain network, all the issues that we have with flooding in Accra, okay, because I haven't even seen one single drainage network, I mean, highways will have it, but they will have it in their own format. They wouldn't want to publish it. I don't know. I mean, we have to go and find out. As long as we keep on having problems, it means we don't have systems that are working effectively. It's as simple as, I don't care what authority you are. You need to make sure you are solving the problem. And GIS helps you to solve a problem. It's a decision support system. Look at this one, is a real network. It's okay. Every single dots that you see there, every single node, or that circle, circle that you see, all the circles you see there, all the circles you are seeing in there are actually junctions. Okay, you can actually drop the train stops at those points. It's okay. The different colors of segments and the lanes are really representing what a particular path through which the train is moving, and then you can alight at a point. This is actually the London Underground. It's very popular in the whole wide world. It's one of the wide, reaching networks that you can ever have. Okay, but I want you to kind of understand this at the basic, that this is what networks, this is what they are. Are you okay? This is what they are. So you can keep going on and on. Power networks, gas pipelines as a network. And the whole idea is that I want to share. So the thing about networks is that they allow you to share, because there are options for reaching so many points. Are you okay? Quickly. That's the whole idea. So when you have one road network from Adenta going straight to Accra Central, and I can't get to Abukobi easily, Agoba easily, then it means this is not any good. This is not fulfilling the purpose for a network. And that's a challenge that we have in Ghana. Are you okay? Like a city like Accra, then we are, when someone chases you, and or if someone hears that you are going to say La Paz, they know by all means you use a particular link. Are you with me? That is really crazy. It's not even good for security. And I hear in some African countries the same thing happens. One route from the bottom of the country to the top. Are you okay? From the south to the north. We need to take advantage of networks and let it work for us. It will work for security, police, work for fire service, work for every ordinary citizen. If you have good networks, are you all right? Not only should we have them physically established, but they should also be modeled, and so that we can understand how their workings and know which road to close and which road not to close. Because when someone comes to the police and they say they want to even get a permit to use a road for funeral or something like that, I mean, the police should be able to assess the situation and say that by closing this road, this is the implication on the other, all other people on the network. So we need to have we need to have data. Are you okay? So there are requirements for any system that really handles data. If the system is supposed to be real time, then it has to be accurate. Are you okay? So if you have a system that tells you where's the traffic right now, then obviously it has to be accurate. The data should be accurate. So there are system requirements and there are data requirements as well. It should be compact in the system. Yeah, it should be compact. Should have address conversion function. So in other words, we should be able to tell where are you on the network, and we get to know you are at 26 Thompson Road, whatever. Okay, it should be topologically correct. So as you've seen from the screen, the whiteboard, you can see that I'm actually looking at a topologically correct model, because if these are not joining, okay, if these arcs, these lines aren't joining very well here, then you have an issue. Okay, the analysis is going to be wrong. So instead of it telling you that you can actually move from here to here, it will tell you something else that you can't. You can only go straight. Then you have a bottleneck. Are you okay? So we need to meet these requirements, and there are a few attributes that not a few, but the more you have, the better. We can keep, for example, I'm looking at road network at the moment. Road conditions, we can look at that. Classification of roads can be saved as attributes. Remember, an attribute is a characteristic. So every object as it is has so many characteristics. So the objects and its characteristics. In this case, the object is the link. Are you okay? Or the node. Are you okay? What we call it in the case of a road, we are talking about junction. Are you okay? Rolling circle at Medina is one, because I'm close to that place. I'm making reference to that. So classification, speed restrictions, all this should be factored into it so that you can really, manage the network very well. We need to keep track of one-way streets, where we can turn, where you can turn. Are you okay? Talking about turning restrictions, there are certain valves that are used in pipe networks that allow water to flow in only one direction or so. Like there are valves like that. So in every network, the more data you have, the more analysis you can do. Okay, so you take note of the various attributes. Okay, so now, yes, in every network, then you realize that we can talk about the length and direction, and all these kind of properties can be associated with the links. Are you okay? So like I said, a link, or we can refer to it as an edge. Are you okay? Depends on where you come from, which country you are actually dealing with. Is okay. So the nodes are used as origins and destinations. I think I've already talked about that. So if you begin at one point and you end at the other, then where you began from becomes your beginning node. Okay, your from node and your to node. So you move from here to here. It's all right. And the only way you can connect to this link is to bring in another one. Okay, so bring in another line with a node. So here there are two nodes at this point. I think I've talked about this again, but I'll talk about it again because we're talking about network analysis. Are you okay? So this is the idea. Please, guys, because our questions are analytical, understanding is more important than just taking some notes. That is why I'm spending time explaining it for you to understand. All right, so here we go. We can have networks which are oriented with directions, and we can have networks in which there are no directions at all. There are networks that are not looped, they are just one way. Are you okay? You can't go and come back to where you started from. Are you okay? But I remember traveling to UK sometime back, and then I didn't know the place very well in London, and I wanted to go out to a place, and their buses move in an interesting way. Okay, they have really a very sophisticated system. And when I started in the bus, before I was aware, I was back to where I started from. Okay, that's a good one for you. So that network is looped. Okay, I'm talking about loops, oriented networks with loops. All right, so here pictorially, you can see this unoriented, that's oriented, there are directions. And we already talked about how the computer is able to figure out directions. And then we have, looped without directions, unoriented with loops, and then we have oriented with loops. Is that okay? So you can look at rivers, for example. Rivers are always flowing in one direction. Are you okay? All right. So they are oriented. Are you okay? They are oriented. Roads, they are oriented. Most of the time, they are looped as well. Roads are okay. You can talk about one-way streets. They are oriented. There's a direction. Are you okay? And you can have a situation where there is no direction per se. We should take note of that one as well. Anyway, so it boils down to you using a software. Are you okay? And behind every software is what we call the algorithm. The algorithm. Are you okay? So an algorithm is a a stepwise way of solving the problem. So you write the instructions in order, in a sequence, and the instructions are executed. But then you start with the algorithm, which is the idea, okay, the set of instructions, and then you now convert it into the software. Are you okay? So now we need to now find a way to solve problems within the network when we are done with the data. Okay, so building the network data set itself is not easy, all right, or it's a whole task that you have to take into consideration. And then doing an analysis on that data is another thing altogether. Are you okay? So one of the things that we want to do is to, for example, find the shortest route. When the Uber driver picks you, he tries to find the quickest, the shortest way because he wants to save fuel. Are you all right? So you can do a whole of analysis, I must say, is okay, on the network. Okay, example, select lanes that take you as far away from the start node as possible, never turning back. So we can do this. So we can program this so that an Uber driver, remember they I don't know if they have a different app that they use. Okay, they can decide, okay, I want you to give me only customers in a certain direction because I want to go back home. The driver wants to go and rest at the end of the day. So you see, you could almost write a program to handle that. So we need to understand the algorithms and are behind all this. People write these algorithms. Are you okay? Essentially, one can search all links that propagate from a node, moving out one link at a time and gradually accumulating the cost of travel in all directions. So that's also possible. One can see to find a route that passes through the fewest number of nodes. So we're talking about if you really want to travel to Kumasi, you don't want to be visiting in Samana and all that. You want to just get to Kumasi. Is all right. So that's what you want to do. So what's the point in you going through some villages that you're not interested in? So in that case, you're avoiding these things, and that happens in countries where they have the multi-modal networks. In other words, you can have networks in which there are different hierarchies of it. It's okay. So you can travel within the local area, and you can also travel maybe interregional. Are you okay? But we don't have money to build even the local routes. We have an issue. So I think we'll talk about this later. 2030 something. Are you with me? So the common question that really is asked is, what is the shortest path? What is the shortest path? So I'm going to show you an algorithm or a program that actually solves the problem of finding the shortest path on a network. Is okay. So you may want to find, like you said, as part of your planning, I want to just get most of the time, you want to find the shortest route from one city to the other. Okay. So Dijkstra comes up with this algorithm, and then he says, okay, why don't you start by showing me the origin, where you want to start from. That is A. And then you want to look at your destination node as well. So this is the network. First, every student who's listening to me should look at this and see why this is a network. That's the first one. And then we cannot start. Is all right. Okay, so now if you look at it closely, we have links. Okay, so these are the links. Are you okay? These are the links, the lines. You can call the lines the links. And then you can see that we have nodes as well. The nodes are these one round things you see here. Okay, but at this point where my cursor is right now, there are about how many nodes? 1, 2, 3, 4 nodes here. So if you don't appreciate that, you need to call me later and then I'll explain to you. It's okay. But basically, you can see that every link is made up of a beginning node and an end node. Every arc has a beginning and end node. This is from the topology. Okay, one of the rules in topological connectivity. So this is a direct, this lecture links with that topic very well. Take note of that. And so that's why we can ask interesting questions in exam where you have this kind of synergy going on. Okay, so we start from A, okay, and then we work our way to J. But then how do you do it? The cost of traversing a network is accumulated from link to link. That is what we do. That's how the program works. So we will look at starting from A. What is the cost of traveling from A to B? We say 3. So this 3 is 3 units. So it can actually be 3 kilometers. It can be $3. So I want you to think outside the box. We are not talking about a road network per se, but then we are just looking at a generic network, and it can represent a road. Is that okay? So you can look at these values at, you know, width of pipe. Remember that if you have a pipe, the bigger it is, the more the higher the flow. Like we can talk about this, the physics of that as well. And so if I want to get from A to J, then I'll have to accumulate the cost. So to take a route that goes from, say, this end to this end, and then from here to here to here, it will cost me 3 plus 3 plus 1. So that will be 7. Is that okay? All right, to take a cost from here to here, so that will be 2, 6, 8. So which one is the shortest route? Will be the one outside. Are you okay? All right, great. So someone will say, okay, it's possible when you get in here, you can also take this route and get that one. Also give me 3 plus, that's 6. So that it tends to be. So the algorithm will have to iterate. Are you okay? Do an iteration and find out. So the trick to doing it is to take in 2 links from the origin from A. We first consider the shortest link, which is going to be this one, A to C. So initially that is selected. Is that okay? And then as we move away from the link, we realize that it's cheaper to actually go from A to B than to go from A through C to B. So now A to B should be considered in as part of the solution. Is all right. So we do that iteration, selecting links. So as you can see in this one, the right hand side, you see that the algorithm has selected these 2 links. Is all right, and then it's keeping track of it on this table. Is that all right? And then yes, we are just moving on from link to link. We extend it, we keep on accumulating the cost. Okay, so over here you can see we are extending our selection, and then we are rejecting, and then we are accepting others to be the shortest link as we go. And then we just want the minimum cumulated cost. Are you okay? The minimum cumulated cost. So we just keep summing it till we get to our final destination and realize that actually the shortest route is this one here. Even though I started by even trying all these ones, this link can easily be what determined. Are you okay? If you actually go through a process of what selection, the way we did it. Is that okay? And then you are done. I mean, basically that's that for the distress algorithm. Okay, so we can now say the shortest path is 5 units. Are you okay? And then we can extract the roots. Is that okay? And then reverse through where we can work our way backwards. In some links, in some networks, moving in one direction is more expensive than going to the other direction. Let's take an example of moving up a slope. You realize that going up the slope is more expensive than going down the slope, but it's the same 2 points. Are you okay? That you're actually traversing. So that is why we're talking about reversing through it. Okay, so but then that is the distress algorithm. Is that okay? And then yep, that is it. Okay, selecting links and going for the shortest path. We can also talk about if you have a question, you can always put up your hand whilst I'm talking so that I can always allow you to ask your question. But I think it's basic. We can talk about the use of heuristics. Is that okay? So heuristics are more like, you know, ways of solving a problem with by eliminating, you know, what some of the options. Are you okay? All right. So if you're solving a problem like I want you to find countries where white people live, and they say get rid of any country where you don't find snow. Are you okay? If someone said, if you're writing a program to solve a problem of where white people live, and you start by saying that get rid of any country where there's no snow, you see, that's a heuristic. That's the idea. It's a way of solving a problem. For imperfect solutions and heuristics, are you okay? So it's necessary to use heuristics in many applications of network analysis to reduce the search space. In other words, you see the way the distress algorithm went, you have to check the link. Is it this one? No, it's not. Go back, check. Is it this one? Go back, check. Like you're iterating, and it will take a long time to solve one problem. So what you do is that you make use of the heuristic. Is that okay? All right. So for example, in an example, giving a link might only be valid if it points towards a destination. For example, in the example, giving a link might only be valid if it points, I think it doesn't sound right, towards the destination. That is, the angle between the link and the line from the node to the destination is less than 90 degrees. Let's assume you are going to Kumasi and it start turning towards, you are in Accra, and you point towards Ningu Pram Pram. Okay, so you are going in the wrong direction there. So you can also tell the program so that it doesn't look at all those places and check whether they are part of. So you reduce the search space. Are you okay? The search space. All right. Wait. So routing, like we said, involves finding shortest routes. Is that okay? For one point through the other, and it's good for emergency services, business journeys, planning route. In fact, it's very good for a lot of things. Once you are moving around, and we all move around anyway. I don't know anybody who just doesn't move and stay at the same place. This is Google Map here, finding the destination, the distance between the shortest route between, I think, my house and then Malam Junction. Are you okay? So here it gives you even options. This is the shortest, 90 minutes, but then you have 32 minutes option too. So it's up to you. Are you okay to choose the one that you want to use? Maybe you want to choose a route that shows the sea. That gets you closer to the sea. So that all this is part of the routing problem. You can see here, I'm just trying to show you I'm trying to model an interchange in a very crude way. Okay. And so you have these nodes, the round circles. The fill circles are actually junctions, intersections. Okay. And then attributes that we may need: direction, restrictions, impedances, IOK, etc. Take note of that. We've already talked about this. Time needed to travel from one point to the other can also become a cost. We can look at that. IOK. All right. One of the problems that need to be solved for a medical doctor, for example, or that man that walks around, that Nigerian who actually sells clothes on their head. I don't know what they call them, but like you realize that they always want to find the shortest route to visit all their clients. Okay, that's different from finding the shortest route per se. So that problem of a traveling salesperson is to reach all their customers. Are you okay? And then come back home with less cost. Otherwise, you'll have to buy a new shoe every time. Are you okay? Because it's costing you more, you're traveling more, you're working more. So the traveling salesman problem is one of the problems that need to be resolved. Is that okay? Okay. So how does it do it? The program will have to now find the different possibilities of reaching the destination and then coming back whilst minimizing costs. So therefore, there's going to be an algorithm that will have to do that. We also have what we call isoclones in networks. Isoclones, iso for equal, clones for time. Are you okay? So isoclones are lines joining points of equal time. Is okay? Just as isobars are for pressure. Are you okay? So obviously, we should be able to relate to isoclones like contour lines or something like that. They are like contour lines that show you like places where you can reach in 5 minutes. Are you okay? So if you drew such a map, it's very, very helpful. Are you okay? It can help you to think that, okay, if I'm a company and I do the isoclone, I can tell which of my staff are actually traveling very far to come to work. Okay, and probably I don't know whether I award them for loyalty or something like that. I can also look at customers who need to be given, some extra incentive, a coupon for visiting in, a particular shop, for example. We can look at that. Okay, so isoclones can be used for that purpose. Yeah, and for any project that you are doing, you may need to do this. It depends on your knowledge. If you know it, you know it. Are you with me? Okay. If you don't, you wouldn't know what to do. Are you okay? All right. So here, a company is actually like rewarding or delivering for free. Let's look at all these tipper trucks that are delivering sand. Are you okay? To the countryside or the peripheries of the city. Sometimes the company that delivers the cement bags also are also asking, where exactly do you want us to deliver it? And then, at their discretion, they say you won't pay anything. At their discretion, they say you pay something. But you see, they've not really done any calculation. They haven't really done any investigation into it. They're just using their hearts. Are you okay? Say, oh, it's far. Don't do okay. We will charge you. Okay, the driver will charge you. And all this adds to the corruption that we're talking about. I'm not talking about, this is a social science topic, but obviously this is an isochrone. Okay, you can see we have the center. This is where we want to start from. Okay, and as we move away radially, you can see that not all points can be reached at the center. It's not as you expect it to be a circle, but it's not. Are you okay? So this is what isochrones are to us. Remember, at the heart of the isochrone is actually a network. A network is a network. Are you okay? So if I open the tap right now, where would the water reach in 5 minutes? So that would be a pipe network situation. Are you okay? That will help you. I think criminals probably like to, look at things like this. They'll be planning, but I think you should rather use this to help your own self. All right. So there you go. Here, the 30 minutes isochrone, this is the region that you can reach within 30 minutes. And then you can reach this region in 15 minutes. Are you okay? As we go. So network analysis, there are issues that also confront it. Are you okay? You have a software that claims to do some network analysis. In fact, I think we will look at one in our practical, which is coming up soon. You will realize that most software can't do any proper analysis, and those that can do a serious one, you have to pay thousands of dollars to get them. So you have to know what you're about before you invest into them. It's all right. So they may claim to do some network analysis operations, but they may not be that good. They only present some capabilities for calculating shortest route, and that's it. You're done. Are you all right? They can't do much. All right. That's because you have to write the program, isn't it? Data need to be up to date, accurate, topologically correct. It's not going to be easy for you. You have to correct. Are you okay? Some lines that are not tangles, lines that are undershoots, tripping them, extending them, making sure you have notes. It's not going to be easy. Are you all right? So you run what we call the topological check, and you realize that there are so many errors. And until all of them have been corrected, your network solution is wrong. Don't go there. Getting data, okay, that is also up to date and relevant is going to be a serious issue for you, because now, how do you get a data? Speed limits for all the roads. Okay, so that is why I think the lack of data in the system, people should have actually been held accountable for it. I almost sound like a politician, but yes, I'm an engineer. Are you okay? Honestly speaking, you can't, get away with this. That we have to now go back and kind of collect all this data. Whilst you were there in your office working in wherever urban roads or highway, you should have made sure that this was done. Are you okay? So that we can now do proper analysis. And then, because it's not all about bitumen and, substructures and stuff. It's always about, doing some analysis, which may not necessarily be about calculating values, soil moisture content and things like that. It's not always like that. You end up building roads and the people are still struggling to use them. Are you okay? So the network data sets, it's very, very key. Okay. And they are suited for modeling transportation networks. I told you I'm in love with transportation. Are you okay? I just love the whole idea. Okay. Because interestingly, you look at ants, even ants have their own way, they have transects, they move around. Are you okay? They have a way of walking around ants. I once actually saw a group of ants. They were really worrying me in the house a lot. And I try to fight them. I'll sweep them, some red ants, you see them coming back in, I'll put some powder somewhere and see them still come. And in fact, at the point I was getting frustrated. There was once I actually came into the house and I saw these about 5 or 6 of them. They were lined up, they were kind of matching. I just figured I was like, I've lost this fight, but even insects have a certain, way. They have networks. They actually have a way of walking around. Are you okay? Even underground, yeah, within the soil, they have networks. Yeah, not to talk about rats. There's a stubborn one here in the house. Yeah, so we need to have the network data set. Build it. If it takes 1 year, build a network data set. You'll be ready for your analysis. Don't rush to do anything. Are you okay? So you have to store connectivity information where you can turn, cannot turn. Of course, it will be updated as we go. Now, take note of this. 41 steps in building a network dataset in Action. I should tell you that building a network dataset is not trivial. Are you okay? And some of the attributes I'll still keep talking about more hierarchy, multi-net, meters, minutes. So